So next, we move on to examples part of motion along a straight line. First, we have the following problem. A car accelerates from 40 kilometers per hour to 100 kilometers per hour in 10 seconds. Assuming that the car accelerated uniformly, determine the acceleration of the car. So here, the problem itself tells us that the acceleration is uniform. You have uniformly accelerated motion. From the problem, the car accelerates from 40 to 100 kph. That means the initial speed is 40 kph. Assuming positive direction, the initial velocity is positive 40 kph, 40 kilometers per hour. That gives us 11.1111 and so on meters per second. The final velocity, therefore, is positive 100 kilometers per hour or 27.77777778 meters per second. The problem also gives us the time of travel of the car, 10 seconds. Assuming initial time is 0, as we've mentioned in the previous video, final time is 10 seconds. Now, the question is what kind of motion the object is undergoing. The problem tells us it is uniform acceleration. The object is undergoing uniformly accelerated motion. For uniformly accelerated motion, you have four equations to choose from. V is equal to V naught plus AT. X is equal to V naught T plus 1/2 AT squared. V squared is equal to V naught squared plus 2AX. And average velocity is V plus V naught divided by 2 and is equal to X over T. So from those four equations, we see that if we use the first equation, V is equal to V naught plus AT, and we compare that with the known values, we see that the only unknown is acceleration, which is precisely what the problem is asking for. Isolating A is equal to V minus V naught divided by T, which gives us 1.66667 meters per second squared. Next, we have the following problem. Starting from rest, a car travels 20 kilometers along a straight highway in 15 minutes. What is the final velocity of the car? The object starts from rest. That means the initial velocity is 0. The car travels 20 kilometers along a straight highway, taking initial position to be the origin or the 0 position. So initial position x naught is 0. That means, and taking again positive direction, the final position x is positive 20 kilometers. That gives us 20,000 meters. The problem again gives us the time of travel, 15 minutes. That gives us t is equal to 900 seconds. Once again, the object is accelerating. As we can see from the problem, the object starts from rest, but the car travels a certain distance. That means the velocity changes from 0 to a non-zero value. And indeed, that's what the problem is asking for. What is the final velocity of the car? The velocity of the car changed from 0 to this final velocity. So that means there is acceleration. The question now is the car undergoing uniform acceleration or is it undergoing non-uniform acceleration? For non-uniform acceleration, the problem typically gives you an equation or graph that describes the motion of the object. And depending on the situation of the problem, you will either have to differentiate the equation or integrate the equation. But here in this example, in this problem, no equation is provided. That means the object is not undergoing non-uniform acceleration. Rather, the object is undergoing uniform acceleration. And again, for uniform acceleration, you have four equations to choose from. If we look at the equation for displacement or position, x is equal to v naught t plus 1 half at squared. Looking at the known values, the only unknown is acceleration. Isolating acceleration, a is equal to 2x over t squared. We are able to calculate the acceleration value. 0.04938271605 meters per second squared. Now, the problem is asking for final velocity. What we have calculated is the acceleration. So the solution is not yet done. If we now move on to another equation for uniform acceleration, the equation for final velocity, v is equal to v naught plus a t. From the given, we know v naught and we know t. We are able to calculate the final velocity v if we know acceleration a. And since we have already calculated a, the equation is complete. We are able to get the final velocity. V is equal to 44.4444 meters per second. Next up is the following problem. A man sees a car without a driver roll by and starts sprinting after it at a constant speed of 3 meters per second. The car has an initial speed of 5 meters per second and is decelerating at the rate of 0.5 meters per second squared. How long before the man catches up with the car? So how many seconds will it take for the man to catch up with the car? Okay, from the problem, we see that the motion involves two objects, the man and the car. Thus, we have two sets of variables for our kinematics. We have variables for the motion of the man and variables for the motion of the car. The problem tells us that the man is moving at a constant speed of 3 meters per second. So V man is 3 meters per second, assuming positive direction. And this is constant. For the car, the problem tells us that the initial speed of the car is 5 meters per second. So let the initial velocity of the car be v car 1, 5 meters per second. The car is decelerating at the rate of 0.5 meters per second. So the car is slowing down. The acceleration is opposite that of the motion. Since V car 1 is positive, opposite of positive is negative. Therefore, the acceleration of the car, A car, is negative zero point 0.5 meters per second squared. And since the problem does not give any equation describing the motion of the car, this tells us that the car with acceleration, the car is undergoing uniform acceleration. So a car is constant. Now for this problem, the man runs after the car. The distance traveled by the man will also be the distance traveled of the car, and the same goes for time of travel. So x man is equal to x car. Let that be just equal to x. And time t man is equal to t car. Let that be equal to just time t. You have two objects moving in a straight line. Don't make the analysis more complicated than it is. When you have two objects moving along a straight line, moving along basically the same line, analyze the motion of each object separately from the other. For instance, analyze the motion of the car separate from the motion of the man. Analyze the motion of the man as if the car is not there, and vice versa. You can unite the two analyses using either x or t, since x is the same for the man and the car, and the same goes for t. And that's precisely what we will proceed to do in the next part of the example. Analyzing first the motion of the man, we see that the velocity of the man is constant at 3 meters per second. So the velocity is constant. That means the man is undergoing uniform motion. And there's basically just one equation for uniform motion. V is equal to x over t. Isolating x, we get x is equal to v man times time. Next, we look at the motion of the car. As mentioned before, the car has constant acceleration. The car is undergoing uniform acceleration. So for the analysis of the motion of the car, we have four equations to choose from. So first, we look at the equation for the position for displacement. X is equal to v naught t plus 1/2 at squared. For the car, that's x is equal to v car 1t plus 1/2 a car t squared. If we now equate this x for the car and the x that we got from the motion of the man, so we are now uniting the motion of the two objects in terms of x, we get v man t is equal to v car 1 t plus 1/2 a car t squared. The only unknown is t, so isolating t, we are able to calculate the time of travel, 8.000 seconds. It takes the man 8 seconds to catch up with the car. And now we move on to the last example. So consider the following problem. The position of a toy car is found to be described by the following equation. X is equal to negative 5t cubed plus 4t squared plus 6. And the unit for x is millimeters. Determine the displacement of the toy car from t is equal to 2 seconds to t is equal to 5 seconds. At the 5-second mark, what is the acceleration of the car? For this problem, the equation describing the motion, in particular the position of the object, is given. This implies that the object is undergoing non-uniform acceleration, and depending on what is being asked for, you might have to either differentiate or integrate the equation provided. So for the first part, letter A, determine the displacement of the toy car from t is equal to 2 seconds to t is equal to 5 seconds. What is provided is the equation for position. So all we need to do is get the position for t is equal to 2 seconds and the position for t is equal to 5 seconds. And if we get the difference between the two, we get the change in position, we get the displacement of the toy car. So plotting in 2 seconds into the equation, we get x1. x1 is equal to negative 18 millimeters. And then plotting 5 seconds into the equation, we have x2. x2 is equal to negative 519 millimeters. The displacement is just the change in position, so delta x is equal to final position x2 minus initial position x1, which gives us delta x is equal to negative 501.0000 millimeters. For the next part, we are asked to get the acceleration at t is equal to 5 seconds. Now, what is provided is the equation for position. We need to get the equation for acceleration. Going back to the two basic equations or definitions of our variables, v is equal to dx over dt and a is equal to dv over dt. If we have the equation for x, we can get the equation for velocity by differentiating the equation for x. This gives us negative 15t squared plus 8t. A is equal to dv over dt. If we differentiate the equation of v, we get the equation for A. So differentiating the equation for v with respect to time, we get negative 30t plus 8. Now that we have the equation for acceleration, all we need to do now is to plot in the value for time, and we get the acceleration for that time value. So plotting in 5 seconds, we get the acceleration at 5 seconds, negative 142.0000 millimeters per second squared. And that's it for now. We'll continue our discussion of motion in a straight line. The next topic is free fall motion. We'll discuss free fall motion in the next video. So thank you for watching.